And as it does, that steam is going to come in and around here. This wheel is now going to start to turn. So now, as this wheel begins to turn, I'm just going to bring this down here. This particular wheel, this one here is where the steam is coming in. This one is rotating. This one is fixed. So it takes the steam and it redirects it, is all it's doing. And it's going to redirect it into the next one that's rotating. I've now got another fixed blade here that once this starts, because this and this are interconnected, so they're both going to roll at the same time. Now once that steam is finished, it now goes up into another static unit, and now if I've got 4 rotors on here, then I'm going to have 4 stages. And that's how we get the steam to move through the unit.
Like pressure in pumps, is it doubled with each stage it goes through?
What you'll find is as the steam begins to move through, it now starts to cool, and it now starts to turn itself, sooner or later will turn itself back into water. So the hotter and the higher the pressure of the steam coming in, then the longer its life will be through the turbine.
Okay.
So it's a little bit different.
Yeah,
But you still have a stage inside your pump, but you're actually pushing water from one impeller to another impeller to give it that kick in the ass. So what we're doing in here is that we're actually looking at velocity. What is the velocity coming through here that begins to turn that unit? Over here on page 33, you can see that this is a section in here. This is a section in here that are steam admission valves. And these steam admission valves are supported by a cradle. So depending on load or no load on a generator, that's how these can move up and down. And that's on my page 33. Over to page 34, you can see your casing. These are the units that fit in the bottom. So they're fixed, and they bolt right into the casing. So when the rotor is installed, then you put the other half on, and it completes the actual circle. You can have a look at page 35. We have carbon seals on these particular units. The stages in here talk about control devices. So a lot of this, men, is just general information. I'm up to page 43. For our apprentices, of course, we go through this in more detail. We have steam admission valves. I'm up here to page 47, so you men can just have a look through this. So that's where we get into the steam turbine, by using steam. Now normally, when you look at the function of a millwright that's going to be around a steam turbine, basically you're the chief's gopher. The chief basically is the first class power engineer. So even for him, they would probably bring in an expert that would oversee a rebuild of one of these particular units. So millwrights basically would do most of the mechanical, setting in, taking things apart, but the chief would inspect that, and then the fellow from the manufacturer would be the one that would overlook the chief. So it's a very specialized part of our trade. But that doesn't mean one day you couldn't be the top dog or you couldn't be the chief. The other one that we look at in here is our gas turbine. This is the jet engine. And again, you know, I'm going through this at a fairly good clip because there's other things I want to get into. So just bear with me here, gentlemen. I want to go over forward to page 63. Now, normally when we look at steam turbines and when we look at gas turbines, we've definitely got a rotor that's attached to a shaft. Now, that rotor is pretty well going to stay in that shaft. But the blading, when you look at it, and this is in figure 57, what you're going to find in this blading is that the most common type of blading is described as the fir tree. The fir tree is second in from the left. Now, that doesn't mean they don't use the other ones, but the fir tree is the one that basically is going to be the better hold, is what we're looking for. Because there's a lot of square inches of area that that unit is going to be holding with. So the fir tree is what you're looking for. Got that over there. Okay. Now, over here on page 67. '67 talks about the more commoner type of prime mover, which is going to be your electric motor. Now, when I do your electric motors, I'm also going to give you some information on some of the things that we find in electricity. So, when you look over here on page 67, so the electric motors actually start on 66, but I've already mentioned the AC/DC, three-phase, single-phase. Now, when you look at your electric motors over here, you've got a frame size. Now, when you look at the frame size of an electric motor, it's based on the diameter of the motor. So you need to know that. That comes into the frame size. Now, when you look at your DC motor, basically your DC and your single-phase AC are very close together. Basically what you've got is, from the left-hand side, you've got an end bell. And you've got a bearing inside that end bell. Now, normally, you also have a little washer in there, and it's a little spring washer. The spring washer is in the opposite side of the output shaft, so it's in here. Now, that little, it doesn't show it in this picture, but there's a little spring washer in there. The next time you get around smaller motors, push on the shaft, and you'll notice that that shaft will move just a little bit, and the spring will push it back out. The purpose of that is so that the motor can find its magnetic center. Now what I've got here is I've got the frame and I've got the field assembly. Now what I've got here is inside I've got permanent magnets. And then I've got my armature over here. On my armature I also have a commutator. That commutator in here is what's going to allow the power to come into the rotor. Then I've got my bearing, and then I've got the end bell. So normally, as a millwright, you may be expected to replace bearings inside an electric motor. The electricians would do a test on an electric motor. What is the best tool that I would use on an electric motor to make sure that the windings are in the best condition?
Destructive testing or
No,
non-destructive?
this is non-destructive. Have you made...
Resistance.
Yeah, so there's two ways we can make resistance. One is going to be with your tester, right? So when you have your tester, what are you going to be able to check with your tester? AC, DC, you can do voltage, you can do amperage. What's the other thing you can check?
Check for opens.
So you check for ohms. And when you check for ohms, you're going to have to make sure that normally when you look at your multimeter, you've got a little battery in there. And that little battery is going to create some... Are you okay? I'm doing lots of blabbering, that's probably why. really what you got is when you look at your multimeter, you've got a battery in there that is supplying its own power to be able to
Or iPod tested.
Are you there, boys?
We're fine. Hold on. Yeah, okay, we're back.
Okay, so when I look at my multimeter, I can check AC, DC for voltage, I can check for amperage, and I can check for resistance. Now, if I'm checking for voltage and amperage, I'm going to use system power to do that. But when I'm going to measure resistance, I've got a little battery in there that's going to create a flow of electrons. Now, that flow of electrons is going to go through wiring, whatever the case may be. So that's going to tell me the resistance. Now, if I'm checking for ohms, and I happen to take those two probes and put them on AC or DC, finished. So absolutely, you don't use the ohm setting by mistake for voltage or amperage. It is one thing. Now, when you look at the amount of ohms or the amount of energy of resistance you're going to have, that battery is only going to have so much power. So depending on the size of it, or depending on its condition, it could maybe give you a bit of a misread. And boy, this has happened to me a few times. The electrician comes along, click, oh, motor's no good. What do you mean so good? Motor's no good, you gotta change it. So I change the motor. Put the new boner back in, doesn't start. Is it the motor? No. So now what he's gonna do is, he's gonna go out and get his megger. So that's a word you need to know for your red seal.
Insulation tester.
And basically what the megger is going to do, the megger is going to give you a complete reading with almost, and in some cases as much as, the amount of energy you can get out of the grid. So it's going to give it a more accurate type of a test. Now normally what they do is they have a magneto. And you turn this magneto.
There's battery ones now too.
There is, and that's going to create a massive amount of energy that's let go, and then it can read for you. So when you're testing a motor for its condition, the best unit to use would be a megometer, or we call it a megger.
Or iPod tester.
Yeah, megger is the term I'm familiar with in the exam. So that megger basically is going to ensure that there's no dinking around, that either the motor's gone, or maybe some of the part of the switch gear's gone, or something's gone.
How do you spell the megger?
M-E-G-G-A-R.
Backwards.
E-R. Megger. It's called a megamometer.
Megger, I believe they use ER.
Megamometer.
Yeah.
Ah,
Megameter. Megameter.
now, when you flip the page over, what you're going to see here is that you have field poles, or you're going to have magnets inside the unit. You're going to have your armature, and you're going to have your commutator. Now normally what you're going to find on the commutator, when you look over on the next page being 69, this is where you're going to have your brush. The brush basically is where the energy is coming in, and it's now going to hit the commutator, and that's what's going to build the electric field within the winding that now wants to chase those magnets that are inside the housing. And that's how we create that rotating movement in there. Now, when you guys look at this, and you look at this DC setup, how many of you men have got a battery drill? Like when you look at those particular setups. Well, basically what you've got is, from the battery, it goes up into a brush, and that brush basically feeds the power in. Now, have you men ever taken a drill, a grinder, and plugged it into the wall, and noticed you got a bunch of sparks on the inside of the housing? Well, basically what's going on is that as that brush sits on the commutator, and it begins, because you've got a single phase motor when you plug it into the wall, and as that commutator gets rubbed, basically what begins to happen is the brush, instead of riding nice and smoothly, it begins to bounce a little bit. Then you get arcing going on in there. So if you buy Milwaukee, or if you buy, who's the yellow guys? DeWalt. Basically what you can do is that if you run into problems with your tool, there's a screw that you can take out, and you can take out the brush, you can clean it up, and then you can put another brush back in there, and you're kind of back to home again. So that's kind of what an example I could give you of this type of setup. Now, there's different types of things you can run into when you look on the bottom of page 69. I can have set up in series, I can have it set up in shunt, or I can set it up in compound. Series is normally where you look at a battery-powered tool. When you look at the DC...
One light goes out, they all go out.
Sorry?
Christmas lights.
Yeah, same idea. And then when you look at your shunt and you look at the compound, basically we can have capacitors on there that can give us a little extra kick of energy. So it depends on the load, what you want to do with it. It gives you some descriptions over here on the next page. You can have a look through that if you like. The other one you're going to find at the bottom of page 70 deals with AC motors. So this is where we get into our three-phase and we get into our single-phase. So when you look at our AC motors, in the middle of page 71, your squirrel cage is going to be the most common. It's the most used motor. That doesn't mean you can't get the other ones. You get a wound rotor, so it's opposite. When you look at a squirrel cage, your windings go around the outside, we call that a stator. And the rotor on the inside is what runs in the magnetic field. Now, when you look at the wound rotor, just an engineer has come up with another mousetrap. So the windings go around the rotor and the magnets are up in the